Hello everyone. In the last lecture we have discussed about equation of state of shock waves. We discussed a little bit about porous materials and alloys and mixtures, that equation of state of those materials, and today we will discuss a little bit about the temperature rise during shock wave, and also we will talk about some complex problems of shock waves and also shock wave attenuation, interaction and reflection. So, shock wave compresses the materials. Shock waves compresses material and so that increases the temperature, or temperature T rises. So, the thermodynamic process at the shock front is considered to be adiabatic. So, this thermodynamic process at the shock front is adiabatic. So, you know what is adiabatic? Adiabatic is no heat or mass transfer from the system to the surroundings. The release from the shock state to the initial state, that means when a shock wave passes through a material, so after the shock front, then the material will after some time come to the initial state, no high pressure, the pressure will be 0. So, that release from the shock state, that means high pressure state, to initial state, that means mostly it is without pressure. That process is isentropic. So, this is assumed to be isentropic. So, isentropic means an idealized thermodynamic process. That is both adiabatic and reversible. So, for solid materials, these shock Hugenoid curve and the release curve, that is release from shock state to initial state, actually they are very close to each other. So, if you draw the pressure versus specific volume curve V. So, what we will see that there will be a shock Hugenoid, which we can draw like this, that is a curve, and then we can have this release curve, something like this. So, let us see this pressure at this point is P1, temperature is T1. So, this curve, first this curve is the shock Hugenoid of the solid material, shock Hugenoid, and then this is the release curve, or we can say release isentrop, because it is isentropic, okay. And we can even draw a Rayleigh line. We know that the Rayleigh line will be a straight line, will be from this point to connect it to the this point. So, this will be, the straight line will be Rayleigh line. So, this part is the Hertz part is the lost energy. So, basically what we saw is the shock Huguenot curve is this one, and then so we have the release curve that is assumed to be isentropic. So, this is the release curve, and here you have volume is V naught because it starts from here, and then here you have volume V 1, and then volume here we have volume V 1. So, here the specific volume here is a V 2, and then the temperature will also be here T naught and T 2. Because T 2 is greater than T naught, that means this V 2 will be greater than the V naught. So, because that is T naught is the initial temperature, and we know the temperature will rise in this process even after the shock state comes to the initial state. So, using Mie-Grenier equation of state and thermodynamic relations, we can calculate T1 and T2. T1 that is related to the peak point, peak pressure point, and then T2 is the at the point temperature after it comes back to the initial state. Okay, and that is all for this temperature rise. So, let us talk about now little bit some complex problems here. So, in the earlier chapters we discussed about the Rankine-Huguenot conservation equations. Rankine-Huguenot conservation equations, and the equation of state. So, that can describe the propagation of shock waves in basically 1D configuration. So, we what we discussed earlier is that is 1D configuration. 1D configuration is a planar shock front, that means this particle velocity up and shock velocity us are parallel. So, this is 1D configuration, but there can be some complex problems. So, in many cases this may not be so simple. This may not be 1D configuration. So, the geometry may be complex, So, complex geometry basically we are talking about the geometry of the projectile here, and then these those simple equations in this case not sufficient. They are not sufficient for these complex geometries, because the complex geometries will result number one curved shock fronts and number 2, it is it may have radially expanded, or we can call spherically expanded shock fronts, and also complex interaction between shock wave and the material. Shock wave and the material. So these are the main features, main aspects of complex geometries. So these type of problems will require numerical solutions, which can only be, it's only possible using computers, using computers. So let us have a example of the complex problem. We will have an example of this one of the complex problem, that means complex problem of shock waves. So this is nothing but the explosively forced projectile. So we discussed about that in one of the initial classes. So we can call it as EFP. So we talked about shaped charges, and we talked about even explosively forced projectile. So what happens is, suppose we will draw this step by step. So this is the target, this is the target, and we have a projectile which is a metal disc. This is the disc, metal disc with explosive here, explosive with a detonator at that point, detonator. So what happens will be, there will be the velocity will hit the metal disc. So what will happen is, again we will draw the second step. This is our target. I will write target as T. This is our target, and our metal disc will take a shape like this when the detonator will detonate the explosive. So this is, let's say, or we can draw some arrows. This is the detonation front, detonation front. So, and finally, okay, we will draw 2 more steps. No, this is not the final one. This is target. So this is step number 1, this is 2, this is 3. So this projectile will get a shape like this. Projectile means the disc, metal disc, got a shape like this, got a shape like this. And so what will happen is, in the final step, what we can draw is, this is the target, this is the target, this is number 4, and what will happen, the target will be, better we will not write T here. So target will be defeated, and then the remaining product of projectile will thrown away. This some material will be thrown out. So this is the penetration, and and then what I wanted to show is this shock wave. This is the direction of the shock wave. So this is the front of the shock wave. So if you see, this front is curved front, that is shock wave front, curved, and also you can see that the radially expanding and the shock waves are going moving, propagating, and along the radial direction. So this is now the problem is complex. It's not like a planar impact where this is we can have like one dimensional system, which is, that means the particle velocity and the shock wave velocity are parallel. So this type of problems, the complex problem, this type of complex problems are difficult to solve by analytical treatment. That may not be realistic or not accurate, cannot solved by analytical treatment. That means we need a computer, we need to do use some numerical methods to solve this. So we need some computer codes. Computer codes are required, and these codes are generally known as hydro codes, because as we know it will have a hydrodynamic treatment. So these are known as hydro codes. Hydro codes are so they are complex, and then we are not going to discuss details about these hydro codes. We are leaving it for you. If you are interested, you can study this chapter number 6 of Mark Mayer's book. So we don't have that much time to cover all those, and this is, I feel, this little bit advanced. So that's why I am leaving this part for you. If you are interested, really interested in this subject, then you can follow it up from that textbook. So with the help of these codes, what we can do is we can design the shape of explosively forced projectile, and also the explosive charge that we will be using, and also we can predict the crater, that means the impression made by the projectile, crater diameter, that means the impression made by the projectile on the target, diameter, and depth, and also optimization of EFP, explosively forced projectile material. So your projectile material, what should be your projectile material, that we can optimize from these using these hydro codes. Also these codes contain first the conservation equations and constitutive equations, and failure models. So conservation equation, as you know, mass, momentum, and energy, and the constitutive equations means materials behavior, under elastic, plastic and shock waves, and the failure models that may include fracture, we will talk about dynamic fracture later, spalling, that means fail of the material after tensile reflected waves that we discussed, and shear bands that also we will discuss later. So, these hydrocodes and these conservation actually equations deal with the conservation equation of fluid mechanics, and also there are the areas like fluid dynamics and gas dynamics are used here in these type of complex problems.